Our sun will one day become a cold, Earth-sized cinder. This white dwarf is the final, fossilized heart of our solar system, and its story is the ultimate mystery written in the stars. By the end of this journey, you will understand the breathtaking fate awaiting our world and gain a profound new perspective on time itself. How does a star die, and what strange legacy does it leave behind in the eternal dark? What would remain of our planets orbiting a ghost of a sun? Join me as we travel billions of years forward to witness the dramatic death and strange afterlife of our own star. When you look up at the sun tomorrow, what will you see? This final, brilliant ember is what astronomers call a white dwarf. It is not a star in the way we think of one today. A white dwarf is a stellar corpse, the naked, intensely dense core of a sun that has run out of fuel and cast off its outer atmosphere in a final, beautiful sigh. All that remains is this searing hot, Earth-sized sphere of matter, no longer powered by nuclear fusion. It shines only with the leftover heat of its former life, a fading glow that will persist for trillions of years. Picture the last, fiercely hot coal you pull from a campfire, radiating a pure white light as it slowly surrenders its warmth to the dark. That is the essence of a white dwarf. But what keeps this cosmic ember from simply collapsing in on itself into nothing? It is held up by a bizarre and fundamental law of the quantum world, a force known as electron degeneracy pressure. In simple terms, when matter is crushed to incredible densities, the electrons within it are forced into the closest possible quarters. They resist being packed any tighter with a kind of unstoppable quantum pressure. This pressure, not the fire of fusion, is what supports the white dwarf against the immense pull of its own gravity. To grasp its density, consider this. A white dwarf contains roughly the entire mass of our sun, but compressed into a volume no larger than the Earth. A single sugar cube-sized piece of this material, if you could bring it to our world, would weigh as much as an elephant. It is matter in its most extreme, compact form, a diamond-like cinder of carbon and oxygen, forged in the heart of a dying star. This is the ultimate fate of our own sun, a transformation from a blazing sphere of light to a silent, dense, and fading jewel in the void. To understand its death, we must first appreciate its life. Our sun was born from a vast, cold cloud of gas and dust, a stellar nursery drifting in a spiral arm of the Milky Way. Something, perhaps the shockwave from a distant exploding star, disturbed this quiet cloud, causing pockets within it to collapse under their own gravity. In one of those pockets, a protostar began to spin and gather mass, a fiery seed in a swirling disk of debris. For millions of years, it contracted and heated until the very core became a furnace of unimaginable pressure and temperature. That was the moment of ignition when hydrogen atoms, squeezed together with such incredible force, began to fuse into helium. This nuclear fusion released a torrent of energy, creating an outward pressure that finally halted the inward crush of gravity. A star was born, and our solar system began to take shape from the leftover material in that disk. That newborn star is the sun we know today. It exists in a state of exquisite and temporary balance, a phase astronomers call the main sequence. For the past 4.6 billion years, and for roughly another 5 billion to come, the sun will remain in this stable chapter. Every second, in its core, it fuses about 600 million tons of hydrogen into helium. The energy released from this ongoing reaction pushes outward with tremendous force, perfectly counteracting the immense gravitational pull that is constantly trying to collapse the star inward. This balance is the reason for our existence. It provides the steady, unwavering light and heat that has allowed life to flourish on Earth. It feels eternal, this daily rise and fall, this constant presence in our sky. But this stability is an illusion of our brief human timescales. The main sequence is not a permanent state. It is merely the longest, most stable act in a stellar drama. The Sun is not burning like a piece of wood. It is a self-contained reactor with a finite fuel supply. Deep in its core, it is slowly, inexorably changing. As hydrogen fuses into helium, the core gradually fills with the inert ash of these reactions. This helium ash does not burn under the current conditions, and so it accumulates at the star's very heart. The balance is delicate, and it is destined to break. The Sun's normal phase is just one quiet chapter in a story that ends in cosmic violence and ultimately in that silent, glowing cinder we call a white dwarf. The fuel will run out, and when it does, the true transformation begins. That delicate balance will finally shatter in about 5 billion years. Deep within the solar core, the last reserves of hydrogen will be exhausted, leaving behind a growing sphere of inert helium ash. With a central fusion engine sputtering out, the outward pressure it provided suddenly weakens. For the first time in 10 billion years, gravity wins a decisive victory. The core, no longer supported by fusion, begins to contract under its own immense weight. This collapse is not the end, however. It is the trigger for a far more violent and spectacular rebirth. As the core contracts, it heats up dramatically, like a bicycle pump warming the air inside it through sheer compression. This heat becomes so intense that it ignites a shell of hydrogen just outside the collapsing core. Our Sun, in its death throes, becomes a layered onion of fire. The hydrogen shell burns furiously, dumping even more helium ash onto the core and unleashing a flood of new energy. This surge of power does something extraordinary. It pushes the Sun's outer layers outward with irresistible force. The star begins to swell, and it will not stop until it has transformed beyond all recognition. This is the beginning of the red giant phase, the Sun's final, glorious, and destructive act. The transformation is both beautiful and terrifying. Over a period of several 100 million years, our familiar yellow Sun will inflate to a monstrous size. Its outer atmosphere will cool, shifting its color to a deep, ominous red. But do not let the cooler color fool you. The surface may be less intensely hot, but the star's total energy output will be hundreds of times greater than it is today. The Sun will grow so vast that its outer edge will reach beyond the orbit of Earth. From the perspective of our baked and barren world, the sky will be filled with a glowing red ocean of plasma. The first victims will be the inner planets. Mercury will be swallowed whole, vaporized in an instant within the Sun's tenuous but searing atmosphere. Venus will follow, its thick clouds offering no protection as it too is consumed. Earth's fate hangs in a strange balance. Some models suggest our planet may just barely escape being engulfed, orbiting perilously close to the stellar surface. But escape is a technicality. Long before the Sun reaches its maximum size, the increasing heat will have long since boiled away our oceans, stripped our atmosphere, and melted the very rock of the crust. Earth will be reduced to a scorched, airless lump of magma, a dead world orbiting inside the extended atmosphere of its dying parent star. The entire inner solar system will be remade in a furnace of apocalyptic scale. This red giant Sun is a paradox. Its outer layers are so distended and thin that, by volume, they are almost a vacuum compared to our air today. If you could stand on what was left of Earth, the red giant would appear as a shimmering, ethereal wall of light consuming half the sky, not a solid surface. Yet, the sheer amount of energy radiating from this swollen giant is enough to sterilize worlds and push the surviving gas giants outward into new orbits. This phase is the ultimate prelude, a violent and necessary step to create the conditions for what comes next. All this expansion, this furious burning of shells of fuel, is merely the Sun shedding its outer identity. The real story, the creation of the white dwarf, is happening in the collapsing heart of this red giant. The core continues to contract and heat under the weight of the star, preparing for one last brief and frantic fire. This final, furious burning cannot last. Deep within the swollen red giant, the core of helium ash has been compressed and heated to an unimaginable 100 million degrees. At this critical threshold, a new and desperate fire ignites. The helium itself begins to fuse, creating carbon and oxygen in a violent thermal pulse known as the helium flash. This sudden release of energy is like a bomb going off at the star's heart, and it sends powerful shockwaves rippling outward through the unstable outer layers. The star, already bloated and tenuous, cannot hold itself together against these internal convulsions. In a series of great, shuddering pulses, the Sun will begin to shed its entire outer atmosphere. This is not a gentle release. It is a stellar wind of epic proportions, blowing away the star's own body into the void of space. Over tens of thousands of years, these ejected layers expand outward, forming a vast, intricate, and breathtakingly beautiful cloud of incandescent gas. We call this glowing shroud a planetary nebula, a name that is a complete historical accident. Early astronomers, peering through small telescopes, saw these faint, round, greenish objects and thought they resembled the disks of distant planets like Uranus. The name stuck, but it is a profound misnomer. A planetary nebula has absolutely nothing to do with planets. It is the funeral shroud of a sun-like star, the final, radiant signature of its death. What we are witnessing is the star's outer identity, its atmosphere that once warmed our world being returned to the galaxy. This process is the sun's beautiful farewell gift, a burst of cosmic recycling that seeds interstellar space with the heavy elements forged in its core: carbon, oxygen, nitrogen. These are the very atoms that will one day become part of new stars, planets, and perhaps even life elsewhere. The nebula glows not from starlight, but from the intense ultraviolet radiation now pouring from the exposed, searing hot core. That radiation energizes the expanding cloud, causing it to fluoresce in brilliant greens, reds, and blues. We can see previews of our own star's fate in objects like the magnificent Ring Nebula. Through a telescope, it appears as a delicate, smoke ring-like structure of glowing gas, but that ring is an illusion of perspective. We are looking at the outer shell of a three-dimensional bubble, a sphere of gas expanding from a central, fading star. That central star is the future of our sun, a white dwarf now revealed in all its naked, blistering glory. For a cosmic instant, this pairing is one of the most stunning sights in the universe. A luminous, intricate nebula illuminated by the diamond-like cinder at its center. But the nebula itself is ephemeral. The cloud continues to expand and thin, and over another few tens of thousands of years, it will dissipate entirely, fading into the general background of the galaxy. All that will remain is the white dwarf, the silent, dense core, now drifting alone in the dark. The beautiful shroud vanishes, leaving behind only the fossilized heart. With the nebula's beautiful glow fading into the galactic dark, only the core remains. This is the moment of the white dwarf's true birth, a stellar fossil now exposed to the cold vacuum. It is a sphere of unimaginable heat, its surface blazing at over 100,000 Kelvin. To compare, our sun's surface is a mere 5,800 Kelvin. This newborn remnant is so ferociously hot it shines with a searing, actinic white light, a pinprick of pure intensity against the black. Yet for all its blistering temperature, it is shockingly small, compressed to a size no larger than the Earth. All that remains is the star's original heart, a dense ball of crystallized carbon and oxygen, the final ash of 1 trillion years of nuclear fusion. This is not a star as we know it. The furious fires in its core have gone silent forever. No more hydrogen fuses into helium, no more helium into carbon. The chain reaction that defined its life has ended. So where does all that blinding light come from? It is the glow of residual heat, the trapped thermal energy of 1 billion years of burning, now slowly leaking into space. Think of a piece of iron pulled from a forge. It glows white, then orange, then red as it cools, radiating the heat stored within its very structure. The white dwarf is that cosmic ember, cooling with impossible slowness across timescales that dwarf the current age of the universe. Its brilliance is not a sign of life, but a memory of it, a luminosity that can only fade. This is the pivotal and permanent transition. The dynamic, balancing act of a main sequence star is over. The violent expansions and pulses of the red giant phase have ceased. What remains is a dormant, ultra-dense remnant settling into an eternity of quiet cooling. It has become an object of profound simplicity and extreme physics, a monument to what our sun will ultimately become. The brilliance of a newborn white dwarf comes from its unimaginable heat, but its true nature is defined by something far stranger. This stellar cinder is not a uniform ball of gas. Its structure is a testament to extreme physics, a layered relic of its explosive past. Picture it like a cosmic onion, but one forged in a furnace of apocalyptic scale. The outermost layer is a vanishingly thin atmosphere, perhaps only a few meters thick. This atmosphere is not like our own. It is composed of the lightest elements left over from the star's final convulsions, often hydrogen or helium, clinging to the surface under the white dwarf's crushing gravity. Beneath this wispy veil lies a deeper layer of liquid helium, and further in, a sea of liquid carbon and oxygen. But the true heart of the object is where things become truly exotic. As a white dwarf cools over billions of years, the incredible pressure at its core, millions of times greater than the pressure at Earth's center, forces the carbon and oxygen atoms into a rigid, orderly lattice. They crystallize. Theoretically, the core of an old, cold white dwarf could be a planet-sized diamond, a single, perfect crystal forged from the ashes of stellar fusion. This is not poetic metaphor, but a real scientific possibility based on the physics of matter under such extreme conditions. It is a diamond of unimaginable scale, cold, dark, and waiting in the eternal night. What prevents this entire structure from collapsing into an even denser black hole or neutron star? The answer lies in a fundamental and bizarre rule of the quantum universe, a force called electron degeneracy pressure. To understand it, think of a stadium packed shoulder to shoulder with people. There is simply no space for anyone to move closer together. If you tried to force more people into that crowd, they would push back with immense collective resistance. Inside a white dwarf, matter is crushed to such a density that electrons, the tiny, negatively charged particles orbiting atomic nuclei, are stripped from their atoms and packed together in a similar way. They become a frenetic quantum sea, and according to the laws of quantum mechanics, no two electrons can occupy the same quantum state. This rule creates an unstoppable outward pressure. It is not heat or fire holding the star up anymore, but this pure quantum mechanical refusal to be packed any tighter. This electron degeneracy pressure is the ultimate support beam, the final line of defense against total gravitational collapse. It creates a state of matter that cannot exist anywhere on Earth, a substance both incredibly dense and eerily inert. This is the substance of the white dwarf, a monument not to fire, but to the cold, unyielding rules of physics themselves. And if this quantum support is so absolute, what could possibly threaten such a permanent-seeming object? The answer lies not in its own stability, but in the company it might keep in the profound loneliness of space. This density is not just a number, it is a physical reality that bends the mind. To hold the mass of our entire sun within the volume of the Earth requires matter to be packed into a state that simply does not exist anywhere in our normal experience. Let us make this tangible. If you could somehow scoop a single teaspoon of material from the surface of a white dwarf and bring it to Earth, that tiny amount would weigh roughly as much as a full-grown elephant. A sugar cube of this substance would outweigh a car. This is not merely heavy, it is a fundamental reordering of what matter is. Every cubic inch is so crammed with atomic nuclei and that frenetic sea of degenerate electrons that it represents the ultimate victory of gravity over empty space. This extreme compression has profound consequences, one of which is the sheer force of gravity on its surface. Standing on a white dwarf is an impossible thought experiment, but if you could, you would be crushed instantly by a force hundreds of thousands of times stronger than Earth's gravity. Not a single structure, not diamond, not the strongest alloy ever conceived could withstand it. Your body would be flattened into a film thinner than atoms. This isn't just strong gravity, it is gravity operating in an extreme regime where it begins to warp the fabric of space-time itself in measurable ways. For astronomers, this makes white dwarfs not just cosmic tombstones, but invaluable natural laboratories. By observing how light behaves as it passes through the intensely curved space around a white dwarf, or by watching how it influences a companion star, scientists can conduct precise tests of Einstein's theory of general relativity. The white dwarf's incredible density creates a gravitational lens, bending the path of light in a way that reveals the very geometry of the universe. So this fading cinder does more than just mark an end. It helps us understand the fundamental rules that govern all beginnings and endings. Its terrible density is a key to unlocking deeper mysteries. And if such an object can exist in splendid, silent isolation, what happens when that isolation is broken? What occurs when this stellar fossil is not alone? But this brilliant white light is a fleeting memory. The defining characteristic of a white dwarf is not its heat, but its relentless, inevitable cooling. It is an ember cast from a cosmic fire, and like any ember, it must fade. The journey from a searing white-hot cinder to absolute cold is the longest chapter in its existence, a descent into darkness measured not in billions but in trillions of years. Initially, the cooling is rapid by cosmic standards. Within a few 100 million years, that blistering white glow will soften to a yellow, then an orange, and finally a deep, dull red. It will become a red dwarf in truth, but not in nature, a cold, dense mimic of a living star. The energy it radiates away into the void is never replenished. It has no internal engine, only a finite store of thermal treasure locked inside its crystallized heart. As that treasure is spent, its light dims. Astronomers can actually chart this process on what they call a cooling curve. By measuring the color and temperature of a white dwarf, essentially determining the shade of its fading glow, they can estimate how long it has been cooling. This turns these stellar fossils into some of the most reliable cosmic clocks in the galaxy. By observing populations of white dwarfs in ancient star clusters, scientists can date the clusters themselves, peering back to the earliest epochs of the Milky Way. Each white dwarf is a silent timepiece, its color a direct readout of its age since the nebula faded. The final stage in this unimaginably long cooling process is purely theoretical, for the universe is not old enough to have produced one yet. After perhaps 10, 20, even 100 trillion years of radiating away its last whispers of heat, the white dwarf will reach thermal equilibrium with the background temperature of space itself. It will stop glowing entirely. At this point, it transitions from a white dwarf to a black dwarf, a cold, dark sphere of crystallized carbon and oxygen, roughly the size of Earth, drifting invisibly through the eternal night. It would be virtually undetectable, a ghost of a ghost, emitting no light and only the faintest whisper of residual heat. This is the ultimate fate awaiting the heart of our solar system. Our sun, the source of all light and life for our world, will one day become a cold, black diamond adrift in a black sea. It is a fate of profound and absolute quiet, a silence so deep and lasting it makes the violent drama of its death seem like a brief, bright spark. This black dwarf would be the final monument, a tombstone for a star and all the worlds it once warmed, persisting in the dark for timescales that stretch beyond human comprehension, until even the slow decay of protons themselves might begin to dismantle its atomic structure. But in the near-infinite loneliness of that dark future, might this stellar fossil ever experience a final, violent disruption? the solar system we know will be utterly unrecognizable. Orbiting that faint, cooling ember will be a collection of dark, frozen worlds, survivors of the red giant's fury but now condemned to an eternal deep freeze. The inner planets are simply gone, vaporized or reduced to scorched, airless rocks orbiting within a tomb-like silence, but further out the story changes. The gas giants Jupiter and Saturn will likely have survived, though they will be profoundly altered. Their brilliant, banded atmospheres, once painted by the warmth of our sun, will have cooled and darkened. The great storms like Jupiter's red spot will have frozen into stillness. These majestic worlds will become featureless globes of frigid hydrogen and helium, their colors muted to deep browns and grays, reflecting only the feeble gleam of the distant white dwarf. Their orbits will have shifted outward, pushed by the sun's lost mass during its violent death throes, and they will now take centuries to complete a single, slow circuit around their tiny, dim master. Their moons, once sites of tantalizing possibility, become tombs of ice. Europa, with its subsurface ocean, will see that vast sea freeze solid into a global glacier kilometers thick, extinguishing any hope of life that may have clung on in its depths. Titan's thick, hazy atmosphere will collapse, snowing out as hydrocarbons onto a surface now locked in a permanent, brittle freeze. The complex organic chemistry that danced across its lakes and dunes will cease, leaving behind a frozen, silent landscape under a pitch-black sky. The asteroid belt, once a realm of rocky debris, will be a field of dark, cold stones no longer warmed by sunlight, their orbits perhaps destabilized by the gravitational reshuffling. Further out in the Kuiper belt, objects like Pluto and its kin become the new inner planets, orbiting in a twilight zone so far from the white dwarf that it appears only as a particularly bright star among millions. The entire system is plunged into a cold so profound it approaches absolute zero. There is no day, only varying degrees of night. The white dwarf provides no meaningful heat, only a pinpoint of pale, ancient light casting sharp, motionless shadows across frozen worlds. This is the post-apocalyptic landscape of our solar system's future, a silent, dark museum where the giant planets stand as monuments to a lost age of light and warmth. The dynamic, vibrant system of planetary motion, gravitational dances, and sunlight is replaced by a static, frozen tableau. It is a haunting vista, a complete and total transformation. The familiar cosmic neighborhood of our textbooks and telescopes will have passed into memory, leaving behind only this ghostly arrangement of dark orbs circling a dying cinder. Yet, even in this profound stillness, a question lingers. Could anything at all stir in such a frozen, lightless realm? The answer may lie not in the warmth of a star, but in the hidden, residual heat of the worlds themselves, and in the strange gravitational tides that might still pull at them in the dark. The fate of a planet is not sealed by fire alone, but by gravity's shifting rules. When our sun dies, it will lose nearly half its entire mass, casting it off in those great winds and the beautiful nebula. This sudden, dramatic weight loss has a profound and counterintuitive effect on the surviving planets. Gravity is the sun's grip on the solar system, and when that grip weakens by half, the remaining worlds are effectively released. Their orbits must expand outward like a ball on a string that is suddenly let out to a longer tether. The entire architecture of the solar system will be violently reshuffled. This orbital migration is not a gentle drift, but a fundamental rebalancing act dictated by the laws of physics. For the outer gas giants, this could be their salvation. Jupiter, Saturn, Uranus, and Neptune will spiral outward to new, more distant orbits, potentially finding stability in the cold dark, far from the white dwarf's feeble light. Their survival is a strong possibility, supported by both theory and mounting evidence, but for the inner rocky worlds, this expansion comes far too late. Mercury, Venus, and Earth will have already been engulfed or utterly sterilized during the red giant swelling long before the sun sheds its final mass. Their orbits, even if expanded, would be empty. The real question then is not about the planets we know, but about the ones we are just beginning to discover in these graveyard systems. Astronomers have now found startling evidence that some worlds do make it through the stellar apocalypse. They detect this not by seeing planets directly, but by reading the chemical scars on the white dwarfs themselves. The atmospheres of many white dwarfs are incredibly pure, composed almost entirely of hydrogen or helium, the lightest elements, but some are polluted. Spectroscopic analysis reveals strange, heavy elements like iron, calcium, silicon, and oxygen, materials that should have sunk into the dwarf's dense interior eons ago. The only plausible explanation is an ongoing rain of debris. These white dwarfs are actively consuming the shredded remains of asteroids, comets, and even planets that were gravitationally destabilized during the system's death throes and torn apart by the dwarf's fierce gravity. We are witnessing the final digestion of planetary systems. Even more astonishing, in a handful of systems, astronomers have detected the subtle gravitational tug of intact, surviving planets. These are not giants in close orbits, but often Jupiter-sized worlds, or even suspected rocky super-Earths, orbiting far out in what was once the frozen fringe of their system. They orbit at distances many times greater than Pluto's orbit today, having migrated outward during the chaos. This proves that planetary bodies, from asteroids to giant worlds, can endure the death of their star. They become dark, frozen nomads, circling the cinder of their sun in a perpetual, silent vigil. The survival of a planet depends on a brutal calculus, being far enough away to avoid the furnace, yet still bound enough to avoid being flung into interstellar space. It suggests that our own solar system's legacy, billions of years from now, may not be total annihilation. Jupiter may still be there, a dark sentinel in the endless night, its frozen moons a tomb for secrets we are only beginning to uncover. Our sun's solitary fate is not the only path for a white dwarf. In the crowded stellar neighborhoods of the galaxy, many stars are born in pairs, locked in a gravitational dance that lasts their entire lives. When one of these stars becomes a white dwarf, its companion often remains, setting the stage for a far more violent and spectacular cosmic drama. This is the realm of stellar vampirism, where a dead star can feed on the living, and in doing so, risk total annihilation. If the surviving companion star is close enough, the white dwarf's immense gravity begins to exert a terrible pull. It can siphon hydrogen-rich gas directly from the atmosphere of its living neighbor. This stolen material does not fall directly onto the white dwarf's surface. Instead, it spirals inward, forming a searing hot, flat structure called an accretion disk that whirls around the dense core like water circling a drain. The gas in this disk is superheated to millions of degrees, glowing with intense X-rays as it is dragged ever closer to the point of no return. For a time, this process can be stable. The hydrogen accumulates in a thin, dense layer on the white dwarf's incredibly hot surface. But this stolen fuel is sitting on a furnace. As the layer grows thicker and is compressed by the dwarf's crushing gravity, its temperature and pressure skyrocket. Eventually, it crosses a critical threshold. The hydrogen ignites not in the steady fusion of a star's core, but in a sudden, runaway thermonuclear explosion that rips across the entire surface of the white dwarf. This is a nova. In a blinding flash, the dwarf can increase its brightness by a factor of 50,000 or more, outshining entire galaxies for a few days or weeks before fading back to its original state. The explosion blasts the accumulated stolen material back into space in a spectacular shell of ejected gas. Crucially, the white dwarf itself survives the ordeal. It remains intact, ready to begin the slow process of accretion all over again. Some of these stellar vampires experience recurrent nova, flaring to life every few decades or centuries as they repeatedly steal and detonate their companion's atmosphere. But there exists an even more catastrophic tipping point. If the white dwarf is part of a particularly close binary and the accretion is rapid and steady, something far more extreme can happen. The dwarf might not just ignite the surface layer, but instead accumulate so much mass that it is pushed over a fundamental limit known as the Chandrasekhar limit. This is the maximum possible mass for a white dwarf, about 1.4 times the mass of our Sun. At this point, the quantum pressure of its electrons can no longer support the crushing weight. What happens next is one of the most violent events in the universe. The entire white dwarf undergoes a complete thermonuclear detonation from the inside out. In a fraction of a second, the carbon and oxygen core fuses into heavier elements like nickel and iron. The energy released is beyond comprehension. This is a Type Ia supernova, an explosion so brilliant and uniform it can outshine an entire galaxy. No remnant is left behind. The white dwarf is completely and utterly vaporized, its atoms scattered across interstellar space. This dramatic binary fate stands in stark contrast to the quiet, solitary cooling that awaits our own Sun. Our star travels through the galaxy alone, with no companion to feed from or be fed upon. Its path to a cold, dark cinder is set, but for a white dwarf with a partner, the story is never truly over. It exists in a precarious state between a slow fade and a sudden, brilliant death, a testament to the fact that in the cosmos, even the dead can be resurrected for one final, world-ending act. That final, brilliant detonation is the Type Ia supernova, the ultimate cataclysm for a white dwarf. This explosion is not a surface eruption like a nova, but a total and complete self-immolation. The trigger is a single critical number, the Chandrasekhar limit. This is the maximum possible mass for a white dwarf, roughly 1.4 times the mass of our Sun. It represents the final victory of gravity over the quantum pressure holding the star up. For a lone white dwarf like the future Sun, this limit is irrelevant. It will never gain mass. But for a white dwarf in a close binary system, it is a cosmic tripwire. If it steadily siphons enough material from its companion, its mass creeps upward toward that fatal threshold. As it approaches 1.4 solar masses, the internal pressure and temperature within its crystallized carbon-oxygen heart become too great to contain. The entire core, under unimaginable strain, reaches a single, uniform ignition point. In that instant, a wave of runaway carbon fusion rips through the white dwarf from the inside out. Every atom of carbon and oxygen fuses into heavier elements like nickel and iron in a flash of energy so vast it defies description. The entire structure, that Earth-sized ball of degenerate matter held together by quantum rules, is completely vaporized. No neutron star, no black hole, not even a fragment remains. The white dwarf is annihilated, its entire being converted into a fireball of incandescent gas and a shockwave of light that races outward at a significant fraction of the speed of light. The energy released in a few seconds rivals the total output of an entire galaxy of stars. It is one of the most energetic and most standardized events in the known universe. This standardization is what makes Type Ia supernova priceless to astronomers. Because they all detonate at roughly the same mass, they all reach roughly the same peak intrinsic brightness. Think of it like a series of identical light bulbs placed at different distances. By measuring how bright the bulb appears from here, you can calculate exactly how far away it is. In the cosmos, Type Ia supernova are these perfect standard candles. By observing their apparent brightness from Earth, scientists can calculate precise distances to the galaxies that host them. It was the study of these distant supernovae in the late 1990s that led to the shocking discovery that the expansion of the universe is not slowing down, but accelerating, driven by a mysterious force we now call dark energy. So, a white dwarf's final, self-destructive act helps us measure the scale and fate of the entire cosmos. Furthermore, this violent end is a crucial act of cosmic creation. The furnace of the explosion forges elements far heavier than carbon and oxygen. It is in these blasts that much of the universe's iron is created, along with elements like silicon and nickel. This material is then blasted into interstellar space, enriching future generations of stars and planets. The iron in your blood, the calcium in your bones, every heavy element in our world beyond hydrogen and helium was forged in the heart of a dying star. But a significant portion, especially the iron, was likely delivered by a cataclysm like a Type Ia supernova. So this explosive alternative fate, while leaving no stellar remnant behind, leaves a lasting legacy in the chemistry of new worlds and in the fundamental measurements of reality itself. The evidence for this strange future is written across our galaxy today, not in prophecy but in cold, hard data. Astronomers have already found thousands of these stellar cinders, and the methods they use are a testament to human ingenuity. White dwarfs are incredibly faint for their temperature, a tiny, hot pinprick against the dark. One of the first clues to their presence is often an anomalous motion. Because they are so dense and compact, a nearby white dwarf can appear to zip across the sky with a surprisingly high proper motion compared to more distant stars, like a single bright grain of sand skimming across a beach. Other times, they betray themselves through their gravitational pull. A star like Sirius, the brightest star in our night sky, was observed for centuries to wobble slightly in its path. This wobble could only mean one thing: an unseen companion was tugging on it. In 1862, astronomers finally spotted that companion, a faint point of light orbiting the brilliant dog star. They named it Sirius B. Calculations of its mass and luminosity revealed the shocking truth: this faint speck possessed nearly the mass of our own sun. The only object that could be so massive yet so dim was a white dwarf. Sirius B became the first confirmed specimen, a reality check for theory, proving that stellar corpses were not just mathematical curiosities but actual inhabitants of our cosmic neighborhood. The true nature of a white dwarf, however, is unlocked by its light. Astronomers use a technique called spectroscopy, splitting its faint glow into a rainbow spectrum. This spectrum is a chemical fingerprint, etched with dark lines that reveal the elements present in the white dwarf's thin atmosphere. From these lines, scientists can read its temperature, often finding surface heats that dwarf our suns. They can also see its composition, which is typically an unnaturally pure signature of just hydrogen or helium, the heavier elements having long since sunk into the dense interior. But as we discussed, some spectra tell a more violent story. The polluted white dwarfs with spectral lines for iron, silicon, and oxygen provide direct forensic evidence of shredded planetary systems raining down onto the dead star's surface. Each observation builds a clearer picture. By measuring the color and temperature of a white dwarf population in an ancient star cluster, astronomers can chart their cooling, turning them into cosmic clocks that date the cluster's formation. Every faint point of white light is a data point, a piece of the puzzle that confirms the life cycle of sun-like stars. This is not mere speculation about our sun's distant future. It is a forecast built on the census of countless stars that have already lived and died. We are surrounded by the ghosts of suns, each one a silent confirmation of the journey our own star will one day take. These silent stellar cinders are more than just tombstones, they are galactic archaeologists. A white dwarf's pristine atmosphere holds a forensic record, a chemical memory of its final days. When we detect heavy elements like iron, magnesium, and silicon in that thin atmospheric veil, we are seeing evidence of a recent and catastrophic meal. This is the debris of shredded asteroids, comets, and even entire planets, torn apart by the white dwarf's fierce gravity and now raining down onto its surface. Astronomers call this pollution, and it allows them to perform a kind of cosmic autopsy. By analyzing the exact ratios of these elements, scientists can reconstruct the bulk composition of the object that was destroyed. Was it a rocky body similar to Earth or Mars, rich in iron and silicon? Or was it a more volatile, rich body like a comet carrying loads of water ice and carbon compounds? Each polluted white dwarf tells a specific story of a planetary system's violent end, giving us a direct census of what kinds of worlds orbited other stars. It is a startling revelation, the idea that we can determine the geology of a planet light years away, not by seeing it, but by reading the chemical signature of its dust on the face of its dead sun. Beyond these individual autopsies, white dwarfs serve as the most reliable clocks in the galaxy. Their cooling is a one-way, predictable process. A hotter, bluer white dwarf is a younger remnant. A cooler, redder one has been fading for a much longer time. By observing populations of white dwarfs in ancient star clusters, astronomers can chart this cooling en masse. The point where the brightest, hottest white dwarfs disappear from the cluster's population tells you how long ago the first stars in that cluster died. This white dwarf cooling sequence provides a direct method to date some of the oldest structures in the Milky Way, like the spherical halo of stars that surrounds our galactic disk. These measurements tell us that the halo is ancient, its white dwarfs having cooled for nearly as long as the universe has existed, confirming it as the fossilized foundation of our galaxy. This dual role transforms our view entirely. White dwarfs are not merely endpoints, they are active historical documents. They record the violent demise of planetary systems, proving that worlds are not rare curiosities but common features of stellar evolution. And they mark time itself with their fading glow, allowing us to piece together the construction timeline of our cosmic home. Every faint, cooling point of light is a data point in the grand story of the galaxy, a story of birth, death, and the enduring legacy of planets and stars. Amidst this silent population, a strange and powerful anomaly exists. Some white dwarfs defy the expectation of a quiet, uniform fade. They possess magnetic fields of staggering intensity, forces millions of times more powerful than Earth's protective magnetic shield. These fields twist the very fabric of space around the star, creating a realm of extreme and bizarre physics. The origin of such ferocious magnetism is one of the great puzzles. One leading theory suggests it is a fossil field, a concentrated remnant of the magnetic strength from the star's previous life. As the red giant collapsed down to its dense white dwarf core, the original star's magnetic field lines were squeezed together, amplifying their strength to incredible levels, like a skater spinning faster as they pull their arms in. Another possibility involves dynamo action generated by the violent churning of material during the star's death throes. Regardless of their birth, the presence of these fields transforms the white dwarf's simple narrative. They do not allow for a placid, even cooling. Instead, the magnetic field acts as a cage, channeling and trapping the thin atmospheric gases. This can create a star with two utterly different faces. On the magnetic poles, where the field lines funnel charged particles, the atmosphere might be held thick and hot, glowing brightly. Meanwhile, at the magnetic equator, the atmosphere could be stripped away entirely, exposing the cooler, liquid interior of the star directly to space. The result is a celestial object with drastic temperature variations from one region to another, a lopsided and strange ember. This magnetism also dictates the final fate of any debris in the system. Remember the rain of planetary debris that pollutes some white dwarfs. Around a magnetic dwarf, that process is not a simple shower. The powerful field can disrupt the accretion disk, forcing the incoming material to flow along magnetic highways directly to the poles. This means the infalling rubble does not spread evenly across the star's surface, but strikes in focused, violent hotspots, altering the chemical signature we observe. Studying these magnetic anomalies is more than cataloging cosmic oddities. It gives us a unique laboratory to understand how magnetic fields behave under conditions of unimaginable density, a physics we cannot replicate on Earth. It shows us that even in death, a star can retain a fierce and complex personality, a final twist in a story we thought was only about fading quietly into the long, cold night. These magnetic anomalies are not the only way a white dwarf can reveal its secrets. Some of these stellar cinders have a heartbeat. They are known as pulsating white dwarfs, and their gentle, rhythmic flickering opens a window directly into their hidden hearts. This is not a violent eruption or a nova's flash, but a subtle, periodic change in brightness, a slow pulse that can take anywhere from a few minutes to over an hour to complete a single cycle. The cause is as elegant as it is profound. The entire white dwarf is ringing like a bell. Powerful gravity wave oscillations are coursing through its ultra-dense structure, causing the star to expand and contract ever so slightly. With each expansion, its surface grows slightly larger and cooler, dimming its light. With each contraction, it grows hotter and brighter. This creates a steady, observable pulse in its luminosity, a cosmic lighthouse with a slow, steady blink. For astronomers, this regular flicker is a treasure trove. It allows them to practice a form of cosmic medicine called astroseismology. Just as a doctor uses a stethoscope to listen to the rhythms of a heart and lungs, revealing the health and structure of a body, scientists use the pulsations of a white dwarf to listen to the interior of a star. Each specific pulsation mode, each different frequency in the star's vibration, corresponds to a sound wave traveling through a different depth or layer within the dense sphere. By meticulously measuring the periods and patterns of these pulses, astronomers can perform an ultrasound on a star. They can infer the white dwarf's mass with astonishing accuracy, often to within a few percent. They can map the thickness of its outer hydrogen or helium layer. They can even estimate the composition of its crystallizing core, discerning the mix of carbon and oxygen that was forged in its final fires. This data provides some of the most stringent and direct tests of our theories about white dwarf physics and stellar evolution. The models that predict how a star like our Sun will die must also predict the precise internal structure of the white dwarf it leaves behind. The pulsations are the ultimate reality check, confirming or challenging our understanding of matter under extreme pressure, of energy transport, and of the very nuclear processes that led to its creation. In the gentle, rhythmic flicker of a distant white dwarf, we are not just watching a fading light, we are listening to the detailed autopsy report of a star, written in the silent language of gravity and heat. That faint, rhythmic pulse will one day fall silent. The ultimate destination for our white dwarf sun is not a quiet glow, but an absolute and final darkness. After trillions upon trillions of years of cooling, it will radiate the very last of its stored heat into the void. At this point, it undergoes a final, silent transition. It becomes a black dwarf. This is a white dwarf that has reached thermal equilibrium with the cold background of space itself. It is a sphere of pure crystallized carbon and oxygen, roughly the size of Earth, drifting invisibly through the cosmic night. It emits no light, no heat, no radiation of any kind that we could easily detect. It is a cold fossil in the truest sense, a monument carved from stellar diamond, existing in a state of near-perfect stillness. The profound fact is this: the universe is simply too young for any black dwarf to have formed yet. Even the very first white dwarfs, born when the galaxy was in its infancy, have not had sufficient time to cool this completely. Their faint red glow still betrays them, so the black dwarf remains a theoretical endpoint, a ghost waiting at the end of time. Yet even this dark monument is not truly eternal. On timescales that make 1 trillion years seem like a blink, the very fabric of matter may begin to unravel. Current theories of particle physics suggest that protons, the fundamental building blocks of atomic nuclei, might not be perfectly stable over such incomprehensible durations. They may decay with a half-life perhaps longer than a 1 followed by 34 zeros in years. If this proton decay is real, then even the ultra-dense crystallized structure of a black dwarf is not permanent. Over these staggering eons, its atomic nuclei would slowly disintegrate. The iron, the carbon, the oxygen, all would transmute into lighter particles and energy, dissipating into a thin, cold haze. The black dwarf, the final remnant of our solar system, would simply evaporate. This connects to the grandest and most somber forecast for the cosmos itself, the concept of heat death. In this ultimate future, all stars have burned out, all black holes have evaporated through Hawking radiation, and all matter has potentially decayed. The universe reaches a state of maximum entropy, a uniform, icy cold sea of diluted particles and radiation, with no gradients of energy left to drive any process, no stars, no life, no change. Our white dwarf and its eventual fate as a fading black dwarf, and then perhaps nothing at all, is a single chapter in that immense story. It is a reminder that even the most enduring structures we can conceive of are temporary against the canvas of eternity. Our sun's journey from a nurturing star to a dark cinder is not just an ending, but a poignant marker in the slow, inevitable winding down of everything. This immense timeline forces a profound shift in perspective. The story of our sun, from birth to white dwarf, spans over 10 billion years, yet the entire history of human civilization is a fleeting whisper in its final act. We are temporary guests in a mansion built for epochs we cannot comprehend. Earth's vibrant era of life, from the first single-celled organisms to the rise of intelligence, occupies a narrow, golden window of stability between the early chaos of the solar system and the coming expansion of the red giant. Our world has an expiration date written in the stars, and with it, the story of humanity as a terrestrial species will inevitably close. This is not a cause for despair, but a call for a grander vision. It reframes our existence from a permanent fixture to a precious, temporary phenomenon, a spark of awareness that flickered for a moment in the cosmic night. Our responsibility, then, may not be to preserve our home forever, but to ensure the story continues elsewhere. This leads to a tantalizing question. Could life find a way even in the cold light of a white dwarf? The traditional concept of a habitable zone, a band where liquid water can exist on a planet's surface, vanishes when the central star becomes a faint, cooling ember. Surface life as we know it becomes impossible, but life is tenacious and it may not need starlight. In our own solar system, we look to the icy moons of Jupiter and Saturn. Europa and Enceladus harbor global oceans beneath their frozen crusts, kept liquid not by sunlight, but by the relentless gravitational kneading from their giant parent planets. This tidal heating generates energy from within. Now, project this idea billions of years into the future. Imagine a frozen Jupiter, darkened and distant, still orbiting the white dwarf. Its moons, though surface temperatures approach absolute zero, might still retain deep, subsurface oceans kept warm by the same tidal forces. The heat source is not the dead sun, but the gravitational dance of the planets themselves. In such a lightless abyss, life, if it arose during the system's earlier, warmer days, could potentially retreat into these subsurface seas and persist for eons in total darkness, sustained by chemical energy from hydrothermal vents. The white dwarf becomes merely a clock in the sky, not a source of warmth, while the real engine for biology ticks away deep inside a frozen moon. This suggests that a solar system's era of habitability may not be a single continuous event, but a series of chapters. An early chapter for inner, sun-warmed planets like Earth, and a later, darker chapter for distant, tidally heated moons. For an intelligent species, survival across these chapters would require a monumental journey, a migration from a dying world to a new, stranger home in the outer dark, or perhaps even to an entirely new star. This is the ultimate cosmic perspective. It tells us that intelligence, if it is to endure beyond the life of its birth star, must become interstellar. Our sun's fate is the universe's gentle but firm nudge. It whispers that staying in one place on one world around one star is a temporary strategy. The transformation of our star into a white dwarf is not just an ending for Earth, it is a lesson written in fire and ice. It teaches that the cradle must eventually be left behind, and that the future of consciousness may lie in learning to sail the immense starry ocean between the lights, carrying the memory of a yellow sun into the endless night. Engineering a future around a white dwarf would demand a radical reimagining of civilization itself. The cozy era of photosynthesis and surface agriculture is over, replaced by a permanent, profound night where energy is the ultimate currency. How might a surviving intelligence born under a yellow sun adapt to this new, stark reality? One possibility lies not on frozen planets but in artificial worlds. Imagine vast orbital habitats, colossal cylinders or rings, positioned at a precise distance from the faint white dwarf. Their power would not come from visible light, but from the star's intense ultraviolet radiation, captured by massive, specialized solar panels tuned to those higher energies. Within these sealed arcs, entire ecologies could be sustained under artificial suns with gravity simulated by slow rotation. The white dwarf itself, though faint, is still a formidable source of heat. Advanced technology might even tap directly into this thermal gradient, using the difference between the star's searing surface and the near-absolute zero of space to generate power through massive heat engines, drawing energy from the cinder's slow cooling for millennia. The star's immense gravity presents another potential power source. A civilization could deploy what is known as a Penrose process, lowering masses into the intense gravitational well near the white dwarf and harvesting the tremendous energy released as matter is accelerated. This would be engineering on a stellar scale, manipulating the fabric of space-time itself to fuel a society. Perhaps the most profound use of the white dwarf would be as a tool for connection, not just survival. Its intense gravity bends light, acting as a natural lens. A future civilization could position receivers at the focal point of this gravitational lens, creating the most powerful telescope or communication device imaginable. It could listen for whispers from other stars with unmatched clarity, or send focused signals across the galactic void, using their dead sun as a cosmic lighthouse to announce their continued existence. This is not mere fantasy, but speculative engineering grounded in known physics. It transforms the white dwarf from a tombstone into an instrument, a power plant, and a beacon. The ultimate message of this thought experiment is one of relentless adaptation. Intelligence that endures must learn to read the new rules of a changed universe, to see resources where others see only a dead end. The white dwarf phase becomes not an ending, but a challenging new chapter, demanding a civilization evolve from planet-bound creatures to masters of celestial mechanics, drawing light and purpose from the fading ember of their ancient sun. The silent, cooling fate of our sun has long haunted the human imagination. Long before science charted the stellar life cycle, storytellers looked to the sky and wondered what would happen when the light finally failed. This cosmic anxiety has given white dwarfs and dying suns a powerful role in our fiction, transforming them from astronomical objects into profound symbols. In Arthur C. Clarke's classic novel, The City and the Stars, the far future human civilization of Diaspar huddles under an artificial sun, while the real, dying star of Earth's distant future hangs in the sky as a permanent reminder of entropy and an ending that cannot be avoided. It is a backdrop of cosmic melancholy, a setting that forces characters to confront the limits of even the most advanced society. The dying sun becomes a character itself, a silent judge measuring the accomplishments of humanity against the vast, indifferent scales of time. This theme echoes in visual storytelling as well. In an unforgettable episode of Doctor Who, the 10th Doctor and his companion find themselves on a planet orbiting a white dwarf, a star that has already died. The story, titled The Satan Pit, uses this setting masterfully. The planet is a cold, dark rock, its only light the pale gleam of that stellar cinder and the artificial glow of a doomed mining base. The white dwarf is not just a location, it is a mood. It represents the edge of the known universe, a place so forgotten and bleak that it becomes the perfect prison for an ancient, malevolent entity. The science is dressed in drama, but the emotional core is real. The white dwarf symbolizes the ultimate isolation and the chilling silence that follows the fire. In video games, this concept becomes an interactive experience. Many space exploration games, like the Elite Dangerous Universe, feature white dwarfs and their more volatile cousins, neutron stars, as navigational hazards and breathtaking vistas. Pilots must carefully navigate the intense gravitational lensing and radiation jets of these remnants, often using them as boost points for faster-than-light travel. This turns the stellar corpse into a tool and a trial, a thing of both terrible danger and immense utility. It captures a very human duality. We see the end of a star and immediately ask, how can we use it? What can its death do for us? This mirrors our own scientific journey, from fear and myth to measurement and potential mastery. At its heart, the cultural power of the white dwarf lies in its symbolism. It is the ultimate memento mori for a solar system. In stories, a dying sun rarely represents a simple catastrophe. It represents the inevitability of change on a scale that dwarfs all human conflicts. It forces characters, and by extension the audience, to ask fundamental questions. What is the value of a civilization if the universe itself will forget it? Does our art, our love, our struggle mean anything against the backdrop of a cooling star? These stories use the white dwarf as a mirror, reflecting our deepest anxieties about time, legacy, and oblivion. They take a complex astrophysical concept and give it a human face, a feeling of loss mixed with awe. By wrestling with these ideas in fiction, we prepare ourselves to comprehend them in reality. The white dwarf in our future is not just a cinder, it is the final chapter of a story we are writing right now, with every choice we make beneath our own still living sun. Silent, invisible light, these stellar cinders scream across the universe in X-rays. To hear that scream, we needed to leave our atmosphere behind, to build an observatory that could see the universe in a light our eyes cannot perceive. That observatory is NASA Chandra X-ray Observatory, a telescope launched into space to listen to the high-energy songs of the cosmos. While our eyes and optical telescopes see the visible glow of a cooling white dwarf, Chandra detects the furious X-ray radiation pouring from its searing surface, a testament to temperatures exceeding 100,000 degrees. This is not a gentle warmth, it is a blistering, high-energy emission that reveals the true, violent youth of these stellar remnants. Chandra peers directly into the heart of the action, transforming white dwarfs from faint points of light into dynamic, high-energy laboratories. Its most profound insights come from watching white dwarfs that are not alone. In binary systems where a white dwarf is siphoning material from a companion star, Chandra observes the superheated accretion disk as it forms. Gas stolen from the donor star spirals inward, heated to millions of degrees by friction and gravitational compression, and it is at these temperatures that it shines brightest in X-rays. Chandra's sharp vision can map this process, showing us the structure and dynamics of matter as it falls toward the point of no return. This data is crucial for understanding the precise mechanics of stellar vampirism, measuring the rate of accretion, and predicting when a system might be pushed toward a nova or even a cataclysmic supernova. One of Chandra's landmark achievements was creating detailed temperature maps of these systems. Instead of seeing a uniform blob of light, scientists could distinguish the scorching hotspot where the incoming stream of material slams into the accretion disk, creating a shock wave that glows fiercely in X-rays. This is like watching the moment a meteor strikes the atmosphere, but on a stellar scale, with temperatures soaring to tens of millions of degrees. Chandra has also captured the aftermath of nova explosions in incredible detail. When a white dwarf's stolen hydrogen layer detonates, the blast creates a shell of ejected material moving at thousands of kilometers per second. As this shell plows into the surrounding interstellar medium, it generates shock waves that heat the gas to X-ray emitting temperatures. Chandra's images of these events show intricate, expanding rings of high-energy emission, allowing astronomers to measure the energy of the explosion, the composition of the ejected material, and the density of the space into which it expands. These observations turn theoretical models into observable fact, confirming the violent, cyclical nature of these binary relationships. Without Chandra's unique window into the high-energy universe, white dwarfs would remain largely silent in their most active and revealing phases. This remarkable satellite, along with other space-based observatories like Hubble and the James Webb Space Telescope, represents more than just advanced engineering. It is an extension of human curiosity. These missions translate the faint whispers and violent screams of the cosmos into data, into images, into understanding. They are the tools that allow us to read the autobiography of a star, written in the invisible light of its death throes. Each precise temperature map, each observed shock wave, is a paragraph in that story, a paragraph we could never have read from the surface of our world. The pristine atmospheres of white dwarfs should be simple, a clean record of hydrogen or helium, yet astronomers keep finding chemical graffiti that defies explanation. One of the most stubborn puzzles is the unexpected presence of lithium. According to our best models of stellar nucleosynthesis, the process of fusion inside a sun-like star should destroy lithium long before the white dwarf stage. This element is fragile, burning up at relatively low temperatures in a star's interior. So when its spectral signature appears in a white dwarf's atmosphere, it poses a direct challenge. Where did it come from? One leading theory points the finger at the very planets the white dwarf is consuming. Rocky bodies like asteroids could be rich in lithium, and as they are shredded and fall onto the star, they could deposit this unexpected element. Another, more exotic idea suggests that certain rare nuclear reactions during the star's final death throes might have produced it. Each polluted white dwarf with lithium is a crime scene, and we are still deciphering how the element got there, forcing us to reconsider the detailed chemical pathways inside dying stars. The mysteries extend far beyond a single element. Even the beautiful planetary nebula phase, that stunning final shroud, holds profound questions about its shape. Our simple model suggests a star sheds its atmosphere in a roughly spherical wind. So why do we see such intricate structures like hourglasses, butterflies, and complex multi-lobed bubbles? The shaping of these nebulae is an active frontier. Astronomers suspect the influence of binary companions, the spin of the dying star, or powerful magnetic fields acting like invisible sculpting tools, channeling the outflowing gas into these breathtaking forms. The Ring Nebula's simple appearance is an illusion of perspective, but many others show asymmetry that demands an explanation. We are witnessing the final, choreographed dance of a star's mass, and we do not yet know all the dancers. Deep within the cooling cinder itself lies another enigma, the precise nature of crystallization. We predict the core solidifies into a cosmic diamond, but the process is hidden from view. Does it crystallize smoothly from the inside out, like a lake freezing over? Or does it happen in fits and starts, with crystalline snow falling inward through the liquid layers, releasing latent heat that might briefly reheat the white dwarf? This internal rearrangement could explain why some populations of white dwarfs appear to cool slower than expected at a certain age, a phenomenon that helps us use them as clocks. We are inferring the internal weather of a sphere of ultra-dense matter purely from the faint glow of its surface, trying to understand a phase transition occurring under pressures 1,000,000 times greater than Earth's core. These are not minor gaps in a settled story. They are fundamental questions about the physics of matter, the chemical evolution of galaxies, and the ultimate fate of planetary systems. Each unsolved mystery is a reminder that the white dwarf is not a closed book. It is an ongoing experiment, a natural laboratory whose results we are still learning to read. The story of these stellar cinders, including the future of our own sun, is actively being written in the data from our telescopes, inviting anyone who looks up to wonder what we will discover next. That crystallized cinder will become the most durable object our solar system ever produces. Long after the planets have potentially evaporated through proton decay, this fossilized stellar heart may endure, a diamond-like monument forged in the final fires of our sun. It is a permanent record, a cosmic tombstone etched with the fundamental data of its creation. To a being capable of finding and reading it in the distant future, this black dwarf would be a message in a bottle from an epoch unimaginably ancient. Its very existence, its mass, its size, and its chemical composition are direct artifacts of the star it once was. By measuring its gravitational pull and physical dimensions, a future scientist could calculate the original mass of our sun with precision. By analyzing the crystal structure of its carbon-oxygen heart, they could deduce the specific nuclear fusion pathways that occurred in its core, reading the history of its life and death in the atomic arrangement of its ashes. This silent, dark sphere holds the fused remains of everything the sun was, a compressed archive of 10 billion years of stellar evolution. It is the ultimate signature of our star, a fingerprint pressed into the fabric of space-time itself. But the record might hold even more subtle clues. The pollution events we see today, the heavy elements raining onto other white dwarfs, suggest our own solar system cinder might bear similar scars. If Jupiter or a major asteroid were to be destabilized and shredded long after the sun's death, the resulting debris would eventually spiral inward. The unique chemical mix of that debris, the ratios of iron, silicon, and magnesium, would be stamped onto the white dwarf's surface before sinking into its interior. In its deepest crystalline layers, there might be a faint, stratified record of that final feast, a ghostly imprint of the planets that once circled it. A sufficiently advanced archaeologist from another galaxy studying this cold relic might not only know a star died here, but could infer that it was once orbited by a complex system of rocky and gaseous worlds. They could reconstruct a basic chemical inventory of those lost planets, understanding that this was not just any star, but one that nurtured a planetary family. Our solar system, in its final form, would not vanish without a trace. It would leave behind this singular, incredibly dense artifact, a time capsule waiting in the dark for a reader who may never come. It is a strangely comforting thought. Long after Earth is gone and every story of humanity has faded into cosmic dust, the physical evidence of our sun's story, and perhaps a hint of its planetary children, remains locked in an almost indestructible form, a final testament written not in words but in the immutable language of chemistry and gravity. From a nurturing star to a silent jewel, the sun's journey is a story of magnificent transformation. It begins with the stable yellow sun we know, a golden age of life that will not last forever. In about 5 billion years, its core will falter, triggering a violent and beautiful rebellion. The sun will swell into a monstrous red giant, its outer atmosphere swallowing the inner planets and boiling away the oceans of Earth. This apocalyptic phase is not the end, but a necessary shedding. In a final, breathtaking sigh, the star will cast off those outer layers, creating a luminous planetary nebula, a fleeting funeral shroud that seeds the galaxy with new atoms. At the heart of that glowing cloud, the true remnant is revealed, a searing hot white dwarf. This Earth-sized cinder, sustained by quantum pressure and not by fire, holds the mass of a star in a diamond-like sphere. It will then embark on the longest chapter of all, cooling across trillions of years, fading from white to red, and finally to an invisible black dwarf, a cold fossil adrift in an eternal night. This entire epic, from vibrant life to absolute dark, is the ultimate expression of stellar evolution, a process that builds and destroys on a scale that humbles all human endeavor. The sheer span of time involved is almost impossible to grasp. Our entire civilization, from its first spark to its last whisper, will occupy less than a blink in this cosmic narrative. This perspective is not meant to diminish our story, but to frame it with profound clarity. We exist in a fragile, temporary window of stability, a golden hour between cosmic storms. The very fact that we can look up, trace this future, and feel awe in the face of it is a remarkable gift. It invites us to see our own time, our own living world under this steady sun, not as a permanent state, but as a precious and fleeting moment in the grand adventure of the universe. What does this ultimate space mystery make you wonder about? Share your thoughts in the comments below. And if you want to explore more cosmic journeys like this one, be sure to subscribe.